Welcome to the second lecture of the semester of the Geotop-A seminar. It's my great pleasure to welcome Yusu Wang from the University of California at San Diego, who's going to talk to us about persistent Laplacians, properties, and algorithms. Yusu, up to you.
Thank you, Catherine, and thanks to everyone who invited me. I mean, it's really great to be able to share with you some of our recent research on studying this persistent Laplacian, this object. So this is joint work with Facundo Mimoli and Zhengchao Wang. I should say that Zhengchao did a tremendous amount of work for this, and my slides, many of the slides also stole from him. I think he, I cannot see, but I think he probably would also be here later to help answer questions. All right, so what is this about? We probably all know Laplace operator. I mean, it can be defined for different objects. Manifold Laplacian, for example, is a second-order differential objects operator defined for functions on smooth manifolds. Okay, and you can also define this for graphs. We have the combinatorial graph Laplacian, which I'm going to introduce shortly. Okay, so this is now an operator. You can think of it as an operator for linear operator for function defined on vertices of graphs. Okay, and the graph Laplacian has been used very widely in spectral graph theory for handling optimization tasks on graphs, doing, for example, like graph partitioning and so on. Okay, now this combinatorial graph Laplacian turned out that you can also define this, extend this concept for simplicial complex K. Okay, so essentially, if you are given a real valued function f on the set of Q-dimensional simplices of a simplicial complex K, then after apply this combinatorial Laplacian to this function, you get another such function back. Okay. And as we'll see later, that this also have interesting connection to the topology of the simplicial complex K. Now, what we are going to talk about today in this talk is a persistent version of this combinatorial Laplacian for a simplicial complex, defined for a pair of simplicial complexes, K included in another complex L. Okay, so this was the concept was originally introduced in a very nice work by Wang et al. Last year. Okay. So basically, essentially, as I said, that you have a pair of simplicial complexes K and L, and you still define an operator on the space K, yet you're going to use the information from L to help with this operator. Okay, so this goes beyond the graph, even though in this example we have a pair of graphs. All right, so I want to share with you some of our recent findings through our study of this persistent Laplacian. We learned quite a bit through this course, and I'm going to introduce the concept of this and some of the properties, including the properties also help us to find efficient algorithms to compute this persistent Laplacian, and also connections to other objects. So it turned out that, as you'll see, that this persistent Laplace kind of sits at the intersection of topological data analysis, spectral graph theory, and the network circuit theory. So it's a very rich object, okay? And while this talk is going to focus on some properties and algorithm connections we found, I think it will be interesting to further study this object to see what are the applications to the broader topological data analysis context. All right. Okay. I mentioned earlier, this is joint work with Facundo Mimoli and Zhengchao Wang, and here is the reference for the talk. Okay, so let me start with just the first introduce what is persistence Laplace. Okay, but let me take one step back. Let's first go from graph Laplacian and then define the Laplacian for simplicial complex. Okay. Now, feel free to interrupt me to ask questions. I cannot really see, so I don't either. You can just unmute yourself and ask directly, or put in the chat window. Okay, now. Suppose we're given a graph. For the time being, let's keep things simple. Let's assume the graph is unweighted. Okay, so we have a graph with vertex sets indexed by n, 1 to n, edges, and so on. The adjacency matrix is just a standard adjacency matrix. You have aij equal to 1 if there's an edge between vertex I and j and 0 otherwise. Okay. The degree matrix is a diagonal matrix where the ith entry of the diagonal is simply the degree of vertex I. Okay. And the combinatorial graph Laplace is simply defined as the degree D minus A, the degree matrix subtracted the adjacency matrix. Okay, so what is the intuition behind this? What is this operator? Well, let's first look at a simple example. Let's say that we have a function, a real valued function defined on the line. Okay, consider a point x. Consider point x. Okay, then the second derivative of x can be written as basically kind of, first compute the first derivative, first order derivative, and then compute the second order derivative. Okay, so you can rewrite this as these two terms. And if I now think that this line is discretized into this is xi, this is xi plus 1, this is xi minus 1, then you can rewrite this roughly to be basically the sum of the difference between x, the function value at xi plus 1 minus f of xi, and the function value difference between f of xi minus 1 minus f of xi. Okay, so in other words, this two term is simply that you take this middle vertex and look at its two neighbors, and then you sum up the function difference with the neighbors. Okay. Now, if we're given a function defined on a graph, okay, then essentially, as you can see, that the Laplace operator applied to this function at vertex I is doing the same. It simply take all the neighbors of I, and then it simply takes all the neighbors of I and simply sum up the difference between this function, the function value at I with all its neighbors. Okay, so intuitively this gives us the negation of the second order derivative. Okay, this is kind of also consistent with the manifold Laplacian view, where the Laplace of a function at a point defined as the divergence of the gradient. Okay, so essentially you're calculating the divergence of all the kind of directional derivative along all these lines. Okay. This. Okay. All right. So this is the intuition of the graph Laplace. Now, the operator for manifold Laplacian encodes rich geometry of the manifold, information of the manifold. In fact, encodes all the spectral structure, the eigenfunctions and eigenvalues, encode all the geometric information about the manifold. For the graphs, the spectral structure of the graph Laplace also encode very rich information about the topology of the graph. Okay, so here's a simple result, which basically says that suppose we rank all the eigenvalues of the Laplace. It turns out the first one is always 0. Then you order them in non-decreasing orders. Okay, then the number of 0 eigenvalues equals to the number of connect components of the graph. Okay, in other words, you can see that basically the null space of the Laplace operator, the dimension of that equals the Betti 0 of the graph. Okay. Now, if your graph is connected, then the second eigenvalue is non-zero, okay? And the second eigenvalue, lambda 2, has a special name, okay, has been studied a lot. Essentially, this measures kind of the so-called algebraic connectivity of the graph, okay? Roughly, it's like the bottleneck connectivity of the graph, whether the graph has any weak link to partition into two parts or not. Okay, and the corresponding eigenvector, okay, is called a Fiddler Vector, and this Fiddler Vector has been widely used in practice to help to partition a graph into two clusters, for example. Okay, so to see why this second value indicate this bottleneck connectivity. The results by Fiddler basically says that if you have a graph G prime, which is a subgraph of G, in other words, G is richer than G prime in terms of connectivity, then the second eigenvalue of G prime is bounded from above by the second eigenvalue of G. Okay, so as you grow your graph, making it bigger and bigger, then your connectivity also increase, then your second eigenvalue also increase. Okay. So this is the combinatorial graph Laplace for the unweighted case. One can easily modify the definition to handle weights. We'll come back to the weighted case later. Okay, so there's an alternative way to view the graph Laplace operator. Okay, it's more like from a topological point of view. We can also view a simple graph G as a one-dimensional simplicial complex with 0 simplices and 1 simplicis. Okay. Now, if we now take the one-dimensional boundary operator, let's take the boundary matrix B. Okay. If you have, this is n0 times n1 matrix, and n0 means the number of vertices and n1 is the number of edges. Okay. Then it turned out that you can rewrite the graph Laplacian simply as the multiplication of B and B transpose. Okay, and if I take it as an so this is intuitively I'm basically I'm composing the boundary operator with the dual of the boundary operator. Okay, and this topological view now allow us to also extend this graph Laplacian to high-dimensional simplicial complexes. Okay. So here is the, I didn't give the reference here, as I see that this is starts from early work from Ekman in 1940s. Okay, the concept. So here, suppose we're given a simplicial complex K, a finite simplicial complex. Okay, let me use SKQ to represent the set of oriented Q-dimensional simplices. Okay, and CK is simply the Q's chain group with R coefficients. Okay, and the boundary operator is denoted in the usual way using the symbol here. And now, so this is the Q's boundary operator. Okay. Now let's also put an inner product. Now, since we're defining everything using R coefficients, let's also put an inner product on this the Q's chain group, this vector space. Okay, where we take essentially we take the set of Q simplices of K as also normal basis. Okay, and then we can use this. This is a dual operator of the boundary operator. All right. All right. So now, with what we just defined is simply, all the notations are here. We have the Q's chain group, and we have the boundary operator that give us map this to the K-1's boundary group, and we also have the dual of the boundary operator to map it back to the Q's chain group. Okay, and the Laplace. The combinatorial Laplacian now for the Q-dimensional Laplace operator now is an operator from the Q's chain group to the Q's chain group, and it's defined as follows. So essentially, I'm just going to draw this here. You just think that, so we start from here, okay? It has two parts, the up operator and the down operator. The up operator will simply first take the dual Q-1's dual boundary operator, go to Q+1 chain group, and then come back using the boundary operator. So this is the up operator. And for the down operator, we first take the boundary operator to the Q-1's chain group, and then we come back using the dual operator. Okay, so you put these two parts together, then you get the Q's combinatorial Laplace operator. All right? All right. So if we, for all of this boundary and dual boundary operator, if we represent using matrices, then and let the B to represent the boundary matrix. Then in the matrix form, we have that the Q's combinatorial Laplace simply have this form. Okay? All right. Now, as you can see that earlier, the graph Laplace, the graph Laplacian that we introduced. So for our input K is a one-dimensional simplicial complex G, okay? Then we can talk about the zeros Laplace operator. And when you have zero Laplace operator, we don't have the down operator, it vanishes. So there's only the up operator left, okay? So we have this equal to the up Laplace operator, and using this formula, we see that this is the same as the one-dimensional boundary operator, the dual of that multiplied with the one-dimensional boundary operator. Okay, so this is the previous graph Laplace operator is simply the special form of this Q-dimensional case for Q equal to 0. Okay. All right. And Ekman proved in the 40s that for any dimension Q, if you look at the null space of the Laplace operator, okay, and then the dimension of that equal to the dimension of the Q's homology group with our coefficients, that basically equal to the Q's Betti number of the simplicial complex. Okay, so essentially this reflects the homology. Encodes the homology group information of the simplicial complex. Okay, this is also consistent with the zero-dimensional case. Essentially, the number of zero eigenvalues equal to the Betti zero of the graph. All right, so now let's see how to extend this to a pair of simplicial complexes, the persistent version of Laplace. Okay, so this is introduced earlier by Wang et al. Okay, so now we're given a pair of simplicial complex K included in L. Okay, we call this a simplicial pair. Okay, and so for each of the complex, we have this the top and the bottom row indicates each of the complex, and connecting them, we also have the inclusion map. Okay. I'm still going to define an operator here, okay? But we want to use the information from simplicial complex L, okay? How do we do that? Well, let's first consider a subset of the Q plus 1's chain group. And what is this subset? This subset simply consists of all the chains from the bigger complex L, or the Q plus 1 chains from bigger complex L, whose boundary actually lies in the complex K. Okay? So these are the chains from the bigger complex, okay? But its boundary lies in the small complex that we're considering. Okay? So this subset form a subspace of the Q plus 1's chain group of L, okay? And by definition now, we can also define a boundary operator from this subspace to the Q's chain group of K by simply taking the restriction of the boundary operator from. So this operator is simply the restriction of the boundary. Oh, oops, that's wrong. It's simply the restriction of the boundary operator, of this boundary operator. Okay? Okay. Now, with this, so these are the maps that we introduced. We can define the persistent Laplace. Let me just introduce this again. So we look at the subspace of the Q plus 1 chain group of L, okay? And so, but we only look at those chains whose boundary falls in the small complex K, okay? And with this definition, we now can define a boundary operator because the boundary of every chain here will fall within the Q's chain group of K. Okay, and then with the boundary operator, we can also define its adjoint operator. Okay, and now to define the Laplace operator at K, for K, okay, we are going to use the down operator remains the same, because once you take the boundary of chains in the Q chain in for K, it goes here. Okay, so the down operator remains the same, but then for the up operator, we're now going to take this branch. Okay, so we're going to take the adjoint of this restricted boundary operator and then the boundary operator back. Okay, so the up operator will use information from the bigger complex L. The down operator remains the same as before. So this is the persistent Laplace operator. Okay, previously introduced by Guowei-Wei's group. Okay, I should point out that this one is not me. It's from Guowei's group. Okay. All right. So we're going to see a little bit about the intuition in a minute. Okay, what this is capturing, right? So let's look at some properties of this persistent version of the Laplace operator. Okay, first, this operator remains positive semi-definite, and when you rank the order of eigenvalues, the first eigenvalue is also 0. Okay, and now remember that in the graph case, the number of 0 eigenvalue of the Laplace operator equals to the number of connect components of the graph. Okay, so now the number of zeros, the number of 0 eigenvalue now equals to, intuitively, so let me just use this example. It basically is that you look at all the vertices from your small complex K, okay? Then you say that how many kinetic components do they lie in the bigger complex L, okay? So for example, in this case, in L, they form 2 kinetic components. They're coming from 2 kinetic components, okay? So the number of 0 eigenvalue equals 2 in this case. Okay, so the multiplicity of the 0 eigenvalue equals to how many kinetic components of the bigger complex L that K intersects. Okay, so essentially, we're considering simplices only from K, yet when we talk about their connectivity, we're using edges from L to define their connectivity. Okay, so that's intuition. So a particularly interesting thing to note is that, for example, this vertex is not really connected to any other vertex, but it's connected to other vertices through some through simplices, through other edges and the 0 vertices from L. Okay, so the orange-colored vertices are from L. Okay, so we're basically looking at that the connectivity of vertices from K, but using all the information from the bigger complex L to decide this connectivity. Okay, so that's the intuition of this persistent Laplace operator. Okay, intuitively, this up operator is like looking at the connectivity of Q simplices through passes in Q through Q plus 1 simplices. Okay, and in this persistent version of the Laplace operator, okay, we're looking at the connectivity of Q simplices, but through Q plus 1 simplices from L, basically. Okay. All right, so this result is analogous to the non-persistent version. Okay, and we also have a result analogous to Ekman's result in capturing the homology. In particular, now, given K and L, if you look at the Q's persistent homology, okay, from K to L, this is basically that you look at the homomorphism from the Q's homology group of K to the Q's homology group of L induced by inclusion, okay, and look at the image of that, and then the Betti number, this persistent Betti number, namely the dimension, the rank of this map, equals to exactly equals to the dimension of the null space for the Q's persistent Laplace operator. Okay, so this is analogous to the non-persistent version where the Q's Betti number equals to the dimension of the null space of the Q's standard combinatorial Laplacian. Okay, so you also, in other words, just by looking at the number of zero eigenvalues of your Q-dimensional persistent Laplace operator, that gives you the Q's persistent Betti number from K to L. And there's also, so the title here is a little bit misleading, but here the results here really is the monotonicity results of the Laplace eigenvalue. Okay, so now suppose you have a sequence of spaces. Okay, let's just look at 3 here in this example. We have 3 spaces indexed by T1, T2, T3. Okay, you also have this monotonicity, namely, you don't have to read the theorem. Basically, what this says is that this, for any fixed k, okay, the case up Laplace operator, the case eigenvalue of the up Laplace operator from T1 to T2 is smaller than from T1 to T3. Okay, and similarly, the case eigenvalue from the persistent eigenvalue from T2 to T3 is smaller than the case eigenvalue of the persistent Laplace operator from T1 to T3. Okay, so you have this monotonicity. Okay. All right. Now, so this is some of the properties, and we're going to see more properties and connections later. But first, let's talk about how can we compute this persistent Laplace operator. Okay. I'm going to describe 2 algorithms. The first algorithm is really just based on the definition of the persistent Laplace operator, and the second one is based on the interesting connection to the Schur complements. All right, so how do we compute this? Well, if we recall the definition of the persistent Laplace, which is simply that we need the down Laplace part is the easy part. Okay, the standard down Laplace operator. Okay, and we know how to set this up. And for the up Laplace operator, okay, we can just follow the definition. If I can figure out what is this space, the space subspace of a Q plus chain group of L, whose boundary lies in K, if I can figure out this subspace, and I can construct this boundary operator to K, then I can compute its adjoint, and then I can just assemble them to get this up Laplace part. Okay, so that's the idea. Okay, so that's one way to compute this operator. And to do that, we would need to find basically a basis for this Q plus 1's subspace of the Q plus 1's chain group of L. Okay, if we have a basis, then if we also find the matrix representation of the boundary operator, okay, then we can assemble the Laplace operator by essentially taking the boundary and the adjoint of the boundary, and we have this in the middle because that essentially you have there's a change of basis happening here. Okay, so this is in contrast with the original non-persistent version, the Laplace operator. This is the form that we have. So here, this will have very similar form, what we see here. The only thing different is that we have a change of basis here. Okay, but the key is that I have to be able to compute a basis of the subspace of a Q plus 1 chain group of L, and we also need to compute a matrix form of this boundary operator. Okay, so how do we do that? Well, so we want to compute, let's say now I want to compute this boundary operator from, let me just write it here. So we want to basically compute the matrix form of this boundary operator from Q plus 1, LK, the subspace, to QK. Okay, so this is what we want to do. Okay, so we want to compute the matrix form of that, which is denoted by B here. So how do we do this? Well, let's start, just look at this illustration here. Let's start with the boundary operator for Q, for L, the Q plus 1's boundary operator for L, okay? So this is the matrix. So the column here indicate all the Q plus 1 simplices in L, and the rows here indicate all the Q simplices in L. But I'm ordering them by first have all the Q simplices in K. So all of this are the simplices coming from K. And here, this part are the simplices coming from in L, but not in K. Okay? So for the columns, the order doesn't matter. Okay, so here this is a cube. This is standard boundary matrix. The only thing that I just rank the rows to have those simplices from K come first. Okay, all right. And now I'm going to do a column reduction of this matrix, just very much like when we compute the when we compute the homology group. Okay, in fact, closer to the persistent homology. Why? Because I'm only going to use a column operation. Okay, namely, I can add two columns, one column to another one. Okay, so we're going to use the column operation till this matrix is in the so-called reduced form. What does the reduced form mean? Reduced form basically means that for every column, the lowest, so for every column, the lowest entry, which is not 0, has to be unique. Okay, so that's what it means that a matrix in reduced form. Okay, so we reduce this matrix using column operation till that the lowest non-zero entry for every column is either this column complete becomes 0 or the lowest non-zero entry is unique. The index is unique. Okay, namely no two columns share the same lowest non-zero entry. Okay, all right. So now that this is in the reduced form, then I'm going to look at all the columns. I need to move this window out of the way. Now let's look at all the columns whose, like this column, whose portion outside the simplest from K are all 0. Okay? So what does this what does such column represent? Well, this represents a Q chain who basically lies in K, because all the non-zero entries are coming from K. Okay? In other words, you can think of this. This is basically a boundary cycle coming. This is the boundary of some Q plus 1 chain from L, yet the boundary of this Q plus 1 chain from L lies completely inside K. And this is exactly what we want to compute. Remember that the space, this is at all the chains in L whose boundary lies in K. Okay? So in other words, this column basically give me one representative. The corresponding column give me one element in this space that we want to compute. Okay, so we collect all such columns. Okay, and it's not hard to prove that all these columns exactly form a basis of this. Okay, so I collect all the columns whose portion outside K are completely 0. Okay, so this is indicated by the blue ones here. And now I'm only going to take the submatrix formed by all these columns, the portion above this line, namely only their elements in K. Okay, so I take this blue matrix, and this blue matrix is exactly my boundary matrix. This is exactly the boundary matrix from this is exactly the boundary matrix from Q1. Okay, so essentially all we're doing here is basically we use the column reduction to by defining this reduced form to be that the lowest one has to be unique, you essentially try to find a basis representation of the boundary so that the element in the boundary comes as early as possible. Okay. Then after you do that, that's the reduced form. You basically take all those columns whose boundary lies completely within K, and those give you a basis here. And then you assemble the matrix, their corresponding columns give you the boundary matrix. Okay? And we also need the basis, change of basis matrix, Z, but that can also be computed through this process, okay, by taking the matrix that you multiplied when you do the reduction. Okay, so this gives us the new boundary matrix, and this gives us the change of basis. This in turn gives us the way to compute the use persistent Laplacian. Okay, the time complexity for this approach, this is essentially very similar to the persistent algorithm, but only for a pair of spaces instead of a sequence of spaces. Okay, so the time complexity can be written in this form. Okay, you don't have to read this very soon. I'm going to give a different algorithm, and then we'll compare the two. We'll explain the time complexity then. Okay, so the time complexity in a nutshell is that this is roughly the time complexity for the persistent algorithm to compute persistent homology. Okay. All right, so this is the first algorithm, which essentially is coming from the definition of this persistent Laplace operator. Okay, I want to now introduce the second algorithm. Okay, this algorithm is very much algebraic. And it's used something called Shu complements. Okay, and this algorithm is also much simpler than the previous one. Okay, all right. So what is the Shu complement? Well, this is the classical object numerical analysis, and it basically arises. So suppose we're given a block matrix, okay, written here A, B, C, D, and then this Shu complement arise when you do the Gaussian elimination of this block matrix. Okay, but in the precise form, so if I have this block matrix, then the Shu complement of this block D, okay, represented by this notation here, okay, has this form, assuming D is invertible. Okay. If D is not invertible, then we can also, you can talk about the generalized Shu complement of D in M, where you replace the inverse of D by the pseudo-inverse. Okay? And it's not hard to see that this quantity comes if you try to try to reduce your matrix to be upper triangular form, okay, by multiplying only a lower triangular block triangular matrix. Okay, so then this exactly comes here. Okay, all right. So why is this relevant for persistent Laplace? It turned out that we show that, let's say that I start with, let me start with the Laplace operator, the standard Laplace operator for the bigger complex L. Okay, so we have a pair of complex K inside L. So we start the Laplace operator for L. Okay, but remember that what is the Laplace operator essentially is basically from the Q's chain group of L to the Q's chain group of L. Okay, so every column and every row here represent a Q simplex in L. Okay, let me order the simplexes so that first you have all the simplexes coming from K, and then you have all the simplexes coming out in L but not in K. Same here, all these are simplexes coming from K, and all of this are the simplexes in L but not in K. Okay. So we just order the column and rows this way. So this we can compute. This is a standard Q's Laplace operator. We can compute it easily. Once we have this, now let's look at this block. This block basically represents corresponding to all the simplices in L, but not in K. Okay, and I take this block as my previous D. So this is A, B, C, D. So this is a block matrix, and this portion is D in my previous slide. And then I simply compute the Shu complement of D in this big matrix L. And it turned out that the Laplace, the persistent Laplace operator from K to L is exactly the Shu complement. So if I call this one M using notation from the previous slide, then it's exactly the Shu complement of D in M. Okay, so that's basically another interpretation of the persistent Laplace from K to L. Okay, and this also suggests that now to compute the persistent Laplace, okay, I don't need to do all those boundary operator, find their representation, and then multiply those the boundary operator and its adjoint and so on. Okay, instead now the computation becomes very simple. I simply take the compute the standard up Laplace, and then I compute the down operator. I computed the Shu complement using this formula here. Oops. Using this formula. Oh, sorry. Using the formula here. Okay. And then we get to the persistent Laplace operator. Okay, so I stated in this algorithm, but really it's rather simple now, the algorithm. And what's the time complexity? Well, the time complexity essentially for the down Laplace, it doesn't change. It's a standard down Laplace, and it takes basically time quadratic in the number of Q simplices for K. Okay, and to compute the up Laplace itself, we need only, in fact, time linear in the number of Q plus 1 simplices in L. But then to compute the Shu complement in order to get the persistent up Laplace, okay, we have to do matrix multiplication and inverse and so on. So that's why it takes a cubic time with respect to but it's a cubic to the Q simplices in L. Okay, and this suggests that the total time complexity of this second approach using the Shu complement has this form. Okay, and how does this compare to the previous algorithm? Okay, I should point out that this n to the q can be improved to matrix multiplication time, which is a slight better than this n to the power of 2.37 and so on. Okay, all right, so how does this compare to the previous approach algorithm? The previous algorithm is this reduction based, and the time complexity is shown here. As we can see that the dominating term is basically this 2, roughly speaking. The difference is that, as you can see here, this is basic cubic in the number of Q simplices in L, while this one has a linear term, but then it has quadratic term in the number of Q plus 1 simplices in L. Okay, so it's like the difference versus that the one is cubic in the number of edges in your simplicial complex. The other one is the linear factor in the number of edges, but then quadratic factor in the number of triangles in your simplicial complex. Okay, so these two are not directly comparable in general, but then for many practical simplicial complex, usually the number of Q simplices can be much smaller than the number of Q plus 1 simplices, such as when we consider like the Ripps complex for dense point clouds. Okay, then as you increase as dimension increases, the number of simplices increases. Okay, in that case, in the case 1, the number of Q simplices is much smaller than the number of Q plus 1 simplices in your simplicial complex. This new algorithm based on the Shu complement is much more efficient. Okay, can be a factor of n squared faster. Okay, so and note that given that we said earlier that the the dimension of the null space for this persistent Laplace operator also gives us the Q's Betti number, persistent Betti number from K to L. Okay, this also in turn gives us an algorithm to compute the persistent Betti numbers in this time complexity. Okay, so this is in contrast with the previous time complexity using persistent algorithm. This is the same comparison as in the previous slides. Okay, in other words, this new approach of computing persistent Betti number is can be much faster if the number of Q simplices in your bigger complex L is smaller than the number of Q plus 1 simplices in L. Okay? Questions? All right. So this is how we compute. So now we see some basic properties of the persistent Laplace operator and also how to compute that. Let me now also point out a few connections to the to spectral graph theory and the network circuit theory. Okay. The first one is connecting to the circuit theory. Earlier, when I defined the graph Laplace operator, I used the unweighted case just for simplicity. Okay, but now I have to talk about the weighted case simply because that the result then would involve the even when you start with unweighted case, the result involve the weighted case. Okay, but it's very similar to the unweighted case. So suppose we have an edge-weighted graph where edges has weights. Okay, now for every edge, now we consider a matrix W, which is basically the weighted version of the adjacency matrix. So if you have an edge between nodes I and J, you put the weights of Ij there in that corresponding entry. Okay, and you also change the matrix D, which is the diagonal matrix. Before, the diagonal entry, the ith diagonal entry, is the degree of vertex I. Now it's simply you change that to be the sum of the total edge weights for edges incident to I. Okay, so with this two modification, then the weighted combinatorial graph Laplace is defined to be D minus W, same as before. Okay, and you still have this topological way of looking at that. This is the if you use the boundary matrix version, this is the operator can be written as the boundary operator times the weight matrix times. So in fact, here this is a little bit misleading. This W, I shouldn't use the same symbol. This is not the same as this. This is actually a diagonal matrix for all the edges. Where each the diagonal entry is the edge weight, corresponding edge weight. Okay, but basically the point being that you still have the same topological view of this weighted combinatorial Laplace operator. Okay. All right. Now, if you consider weighted graph, you can also view this graph as a circuit network. Okay, electrical circuits. So in particular, for every edge, E, okay, you can view its edge weight to be the electrical conductance. You can think of the edge to be a resistor, okay? And then the weight of this edge is simply the conductance of that resistor. In other words, the resistance of that resistor is 1 over this edge weight, okay? So now a graph can be viewed as this collection of resistors connected through at certain nodes and so on. Okay. Now, given any two nodes, Ij, let's say 1 and 2 here, okay, you can define the so-called effective resistance between these two nodes. Okay. So it has the precise form here, defined using the Laplace operator, but the physical meaning of this effective resistance is basically, imagine that you consider them to be terminals. They connect to some electrical source with a fixed potential difference, okay? And then you see that what is the induced current going into 1, coming out from 2, and then just use the Ohm law to compute the resistance to be potential difference over the current. Okay, that's it. Okay, so So this is physical meaning, but you do have a simple formula to compute this effective resistance using the Laplace operator. Okay? And now, if we're given the electric circuit, okay, we can actually reduce this. Let's say, suppose I only care about vertices 1, 2, 3. Okay, I can actually reduce this circuit to another circuit. Okay, I have to update all the resistors here. Okay, but this new circuit will give you the same effective resistance between all these nodes 1, 2, 3. Okay, so in general, this can be done, and this can be done through the so-called Kron reduction, which I'm going to show you in the next slides. Okay, and after this reduction, you can think that from graph point of view, I started with the graph. Now I get a new graph on a subset of nodes. Okay, but this and the weight is a new weight to the graph. Okay, but the effective resistance between all these nodes 1 to 3 are preserved. Okay, and as I said, it turned out that you can always do that. Okay, so given a graph L, okay, and suppose now I care about only a subset of vertices in your bigger graph L, okay, it turned out that there always exists a new graph spanned by this subset of vertices, okay, this new graph will be a weight to the graph, okay, so there exists a new weight to the graph such that the effective resistance in this new weight to the graph, in this reduced graph, is the same as the effective resistance in the original big graph for all pair of vertices in this new graph. Okay, in other words, no matter what subset of vertices you care about, I can always reduce the original graph to only a graph spanned by the subset of vertices, which preserves the effective resistance. Okay, so this process can be made explicit, but effectively, what happens during this reduction process, if you look at what happens, it turned out that if you look at the corresponding Laplace operator, it's exactly performing this Shu complement operation to get the new weight of the graph, the Laplace operator of the new weight of the graph equals to the Laplace operator of the original graph, the Shu complement of this block matrix as we mentioned earlier. Okay, so this is already well known. Okay, so one of the references is what I'm giving here. Okay, and connecting to what we talk about, we now also know that this Shu complement also equal to our persistent Laplace. In this particular case, this is the graph case. So in this, this is the zeroth persistent Laplace. Okay, in other words, what are we doing in the persistent Laplace, at least for the graph case? Well, we're exactly performing the Kron reduction, basically. Okay, so the persistent Laplace operator that we obtained, this also means that the persistent Laplace operator that we obtained actually is the real Laplace operator for some other weight to the graph spanned by your the subset of vertices. Okay, such that in this new weight of the graph, the effective resistance are always preserved. Okay, essentially, when you look at the persistent Laplace from K to L, okay, it actually retains all the information of the effective resistance for the bigger space L. All right, and it turned out that you can also extend, okay, this effective resistance just using this formula here in equation 1 and to simplicial complexes. And then you have the same result that it kind of preserves this high dimensional effective resistance. It should be effective resistance, not distance. Okay, so you can extend this to high dimensional case, and then you have a result that your persistent Laplace basically preserves this high dimensional effective resistance distance. Okay. All right, so let me also just here introduce a concept called effective resistance between sets, because then I'm going to use now using this to connect to the spectral graph theory. So effective resistance that I introduced just now is defined for a pair of nodes, terminals, okay? But if you have two disjoint sets, A and B, okay, A and B here, you can also define the effective resistance between these two sets, okay? Essentially, this is the same meaning. You can imagine that for all the terminals in A, you kind of connecting them to one side of an electric source. And then here you connect to another side of the electric source, okay? And then you compute the current going through, and then compute the resistance using the potential difference over the current, okay? Alternatively, you can think that I'm going to collapse this set into a single node and update the resistance or conductance of all the edges accordingly, and then just look at after I collapse them, I look at the corresponding effective resistance between these two super nodes. Okay, that's how we define the effective resistance between two sets. Okay, and previous results turn out to also imply that when you take two sets, then the effective resistance between sets are also preserved after the crown reduction or after the Shu complement. Okay. So now I'm going to use this effective resistance for sets actually connect to, as I said, to some spectral graph theory. And the quantity we're going to look at is the so-called Cheeger constant. Okay. So the Cheeger constant for graphs, which is a very widely studied object, essentially is measuring the bottleneck connectivity of a graph. Okay, so if you look at the definition here, it basically says that, okay, I'm going to partition my graph. So given a graph G, okay, I'm going to partition it into A and the complement of partition all the vertices, okay? And for each of the partition of the vertices, I'm going to look at the crossing edges between them, okay? So consider the unweighted case. I'm just going to look at how many edges are crossing between these two, okay? And then I find the best partitioning that minimize this ratio, okay? Essentially, what does that mean? I'm looking for the best partition such that kind of the cross connection is the weakest. Okay, and this ratio is called the Cheeger constant. Okay, so this essentially is a measurement of kind of the edge expansion, again, the bottleneck connectivity in this graph. Okay. All right. So this is just an example of a Cheeger constant, and the Cheeger constant is related to the eigenvalue of the Laplace operator for a connected graph. Then if you look at the second eigenvalue that we mentioned earlier corresponding to the Fiddler vector, okay, then we have the following result that the Cheeger constant relates to this, with this so-called Cheeger inequality. Okay, so here in this formula, D max is the max degree of any vertex in the graph. Okay, now suppose I want to extend this bottleneck connectivity for a high dimensional case and for the persistent case, let's say. Okay, right. There's actually some difficulty in how am I going to define this crossing the crossing edges between two sets in the persistent setting. Okay, so remember that in the persistent setting you have K and you have a bigger space L. Oops. Okay. Now you find a partition of K, A and V minus A, Vk minus A, okay? But you want to look at the crossing between them using information from L, okay? So how do we really extend this concept of crossing edges in this persistent setting using information from L? Okay, that is not very clear, okay? On the other hand, if you think about what is this crossing edges in the in the non-persistent version, just the standard version. Okay, and it's not hard to convince yourself that this is nothing. The total sum of edges crossing from A to V minus A actually can be written as that you are looking at this effective resistance between set A and the complement set, okay, and the inverse of that. In other words, this is like the effective conductance from set A to V minus A, okay? And this is rather easy to prove, okay? And using this now, we can extend this Cheeger constant to the persistent version. In particular, the Cheeger constant is defined as that you're looking at all the partitioning of K, and then you look at the the total weight of the crossing edges divided over the cardinality of these two sets, okay? And this total weight of crossing edges can be rewritten as the effective resistance, inverse of the effective resistance between the two sets. Now, we can simply define the persistent version of Cheeger constant for a pair of graph K to L to be that now you are just looking at still the set A and the complement of A in K, but then you're looking at the effective resistance in bigger graph L, and then you take the inverse of that. Okay, so this is this quantity still represent, essentially this quantity represent that for the partition, let me draw the same picture here. So this is K, this is L. This quantity basically says that for a partition A and the Vk minus A, okay, we're looking at what's the connectivity between these two disjoint sets, but using all the edges potentially, so it can be connected through a sequence of edges in L. Okay, so we're using edges in L to look at the connectivity from A to V minus A. Okay, and this is encoded in this effective resistance of these two sets in the bigger graph L. Okay, all right. So this is the new definition of the persistent Cheeger constant, and under this definition, you have an analogous result to the Cheeger inequality that we seen earlier. Okay, so it have very similar form. So this new persistent Cheeger constant, it also relates to the second eigenvalue of the persistent Laplace from K to L using the same similar type of inequality. Okay. All right, so I think I already went over time. So here I introduced some of a recent investigation of this persistent Laplace operator. As you see that the concept was proposed pretty recently, but at the same time we find this persistent Laplacian to be a very rich object that connecting applied topology, algorithm, spectral graph theory, and circuit theory, and so on. And what I'm presenting here clearly is only one small step. And through the course, when we were investigating this, in fact, we learned quite a lot, including all this connection to other fields. And but there are many open problems for the persistent Laplacian, including that how do you define the persistent Laplace for not just a pair of simplicial complex connected by inclusion, but connected by say simplicial maps, okay? Or what is the right continuous limit of these objects in the manifold case? And very importantly, now we have the concept and we have the algorithm to compute that. How can we really use the persistent Laplace operator to help us in, say, data analysis? Okay, I'm sorry I went over time, and thank you for your attention.
Thank you very much, Yusu, for a very interesting talk. Are there any questions? Are there any questions for Yusu? Or you can leave a question in the chat, or do you have any questions? So maybe I can ask, was there a particular application that motivated you with starting to think about persistent Laplacians?
Right. I think, I mean, the one of the original one, which we haven't really explored yet, is uh, basically the clustering, for example, when you have it's kind of in the semi-supervised setting when you have points that as high density points, but then when you talk about their connectivity, you may actually want to use all the points that you have, even with those. It's like in the semi-supervised setting, you have certain points that probably you know their label, their face for, but when you talk about their connectivity, you want to use all the other points as well. Okay, so this is like you are considering certain a subclass of the object, but when you talk about their relation, you want to use all the a bigger space. Okay, so this is very much in the setting that you have K, which is a subset of points we're interested, but the L, which includes more points, including more edges connecting them. Okay, so in general, it's kind of, I think it's an interesting question that you could have a big space, L, okay, like a, and, but maybe what, that's a host of that's a space of interest. But then maybe the subset you are interested in, the set you are interested in is only a subset of L. Okay, let's say only a subset of edges there. Okay, yet when you look at the relation, let's say you're looking at a random walk along this simplices, you still want to use this as a host space, right? Imagine you have a manifold, the manifold is large, but I only want to know the relation between a few subsets in this manifold. Okay, yet the connection has to still go through the entire subset. Okay, so the question becomes that how do we study the relation of a smaller space in the broader scope of a bigger space? That was what motivated us to look at this.
Okay, thank you. Are there any other questions?
I have a question.
Derek?
Yes, can you hear me?
Yes.
Thank you very much for your talk. I had a question about the definition of the persistent Laplacian. So it seems like there's a bit of asymmetry in this definition. I think the up Laplacian, you use this modified Laplacian, but down you just use the Laplacian for k. I'm wondering if there might be a way to sort of flip that, and if there would be any difference in any of the properties that you would get.
So this is a very good comment. So in fact, as I said, that as we studied all the subjects, we also are learning a lot. So one thing that I should point out is that even though that the Laplace operator defined was the up and the down part, okay, if you really think about it, I mean, these two parts are encoding very different information. Okay, so in fact, it takes some time to, well, still I haven't, even though that we know that the kernel, when you put this down and the up part together, then the kernel space is related to the dimension of the homology, okay? But then other than this, I'm still having a difficult time trying to see why these two parts should even come into the same operator. Okay, and in the field, I think there are people, for example, only use the up Laplace because at least you know from a random walk point of view, right? Then you can think that this is basically I'm looking at the connection between Q simplices through Q plus one simplicity. And this is a more clear interpretation, just like the graph case, what this is doing. Okay. I guess I'm pointing this out just to show that even in the operator itself, these two parts, yes, the formulation looks like they're symmetric, but there's some disconnect between these two parts. Okay, yeah. So right now we didn't see a good way to also, because the down operator, because the way that it's defined right now, naturally, we don't see a natural way to extend it to include the bigger space also into this. It'll be interesting to see whether that can be done.
Yeah, thank you very much for the answer. I guess I was thinking that, I mean, in your definition of this modified chain complex, rather than requiring that the boundary has to be in the smaller simplex, what if you took like the adjoint of the boundary to be in the smaller complex? And in that case, the definition of the corresponding Laplacian, I think the up and down would be flipped.
So you basically say that, I mean, so right now, okay, well, we're looking at everything from the chain group point of view. So if you actually just take the dual space, look at the co-chain group, right? Mm-hmm. So you're saying that maybe then you're only now using the down part now. Is that what you're suggesting?
I guess the suggestion is to flip the role of the up and down part, as in which one you would use this modified Laplacian, the modified boundary map, and which one you would use the boundary map for the smaller complex.
Right. So would that not be equivalent by looking at the co-chain group and then think that now?
Okay, yeah, they might be equivalent. I just wasn't sure.
But then you would have, so that you still don't have it symmetric, right? You would have it only for the downside, right? Yeah, so yes, I mean, right. I do not know how to put them both into a single operator. Yeah.
Okay. Yeah. Thank you.
Okay, thank you. Any other questions? Rollo? I don't know what you're...
Yes, thank you for the talk. I am a PhD student at the University of Chile, and I'm working on topological data analysis for classification without using any other machine learning stage. So my idea is to use a filtration and to build a relationship between data, and then using persistent homology to figure out which topological features could help me to extract a subcomplex. And then I use that subcomplex to propagate labels from labeled point to unlabeled points. But in that construction, I use the epsilon values as an inverse distance factor, and also a locality outlier factor, because epsilon values is an encoding of the distances between points. Yeah? But I was wondering if there is a relationship between your persistent Laplacians and the epsilon values, because when you explain the persistent Laplacians over weighted simplicial complexes, I was thinking what happens if I use the epsilon values as weights in my filtration or in my simplicial complexes. So maybe your persistent Laplacian could help me to extract a better suited subcomplexes to perform the label propagation stage. Okay. I don't know if the question was clear.
Yeah, right. Yeah, thanks for the question. I'm not sure I have a good answer. So right now, for the persistent Laplace, we mostly look at it in the more abstract setting where the input symmetrical complex and the weights are given. And there are, of course, many ways to set up the weights. For the case of clustering, for example, what you set is a reasonable way to set that the weights between two nodes can be their distance. Okay. Let's see. The distance, do we need a distance or do we need the similarity? It's either the distance or you want to change that to be similarity between two.
Yes,
okay?
Yes. I mean a proximity function.
Yeah, right. So one could use that as how exactly to immediately apply the persistent Laplace to the problem you just mentioned. I don't yet see clearly. It could be that you can maybe use once you find the smaller complex, maybe you can use the persistent Laplace to help you to do the label propagation. I'm not sure. There actually, in the archive paper, I think we referred to, there's some work where people use the one-dimensional Laplace, basic between edges and triangle, to do clustering. I forgot the name of the paper, but it should be in the archive paper, which could be relevant to what you want to do. So they are doing clustering, but not just over the point sets. They're using the edge information as well. I don't know whether Zheng Chao, is Zheng Chao there or not? If he's there, I don't know whether he has something to add to this.
Well, I can
Thank
add
you.
some reference. I know there are some people using short comparison to do label propagation.
Mm-hmm. Yeah, Zheng Chao, if you want to put the reference in the chat window, that could also be useful. Yeah. Thank you, Zheng Chao.
Okay. Thank you for your questions. Since it's already 6 where I am and 9 where you are, Yusu, I'd like to suggest that we call it a day for now. Thank you very much for a very interesting and question-provoking talk, and wish everybody a very good weekend, and look forward to the next Geotop-A seminar. Thank you very much.
Thank you all.
Bye-bye. Thank you, Yusu.
Bye. Thanks.